Welcome back everybody to the last video for Chapter 4 for atomic structure. This is still going to go in your 4.3 notes. It's the last half of it. This is part 2 of the video, and in this video we're finally going to be getting into isotopes. So we already looked at these objectives from the last video, but I just want to remind you that particularly now we're focusing on these last two objectives, calculating the atomic mass of an element, and then explaining why elements use the periodic table. But really, we're calculating the atomic mass and identifying isotopes. That's the big idea here. So before we get into a formal definition of isotopes, I just want to review this idea about Dalton. So Dalton was wrong about all elements of the same type being identical. So when we have atoms of an element, they can be slightly different from each other. Remember, the thing that makes an element is the number of protons. So all atoms of an element will have the same number of protons, but it may have different numbers of neutrons. So atoms of the same element can have a different number of neutrons, and then we'd refer to that obviously as an isotope. And then in the next chapter, we'll also be talking if they have a different number of electrons, which is possible, we would call those ions. But today we're focusing on isotopes. Thus, since they have a different mass number, these are called isotopes. And now you might be wondering, well, where did this mass number business come in? Remember that the mass number was equal to the number of protons plus the number of neutrons. So if I'm changing this number of neutrons, of course, this mass number is going to be different. So if I change this, this will be different. So Soddy in 1912 proposed this idea of isotopes, and he said that isotopes are atoms of the same element having different masses due to the varying number of neutrons. So just like we said on the last slide, if we have the mass number and the number of protons, if we change this number is definitely going to change in this equation. And this was a really important idea, and in fact, Soddy won the Nobel Prize in Chemistry in 1921 for his work with isotopes and radioactive materials. So when we name an isotope, or one way that we as students might figure out, well, is this an isotope, is it not an isotope, is if we look at the periodic table, and especially this, we're going to talk about carbon. So when I look at the periodic table, we generally say that the mass number for carbon is 12. We've done lots of calculations where we said the mass number of carbon is 12. But now if we look at this, we're saying carbon 14. So we're now saying that this particular carbon atom has a mass of 14. So this is obviously different. So what we had said before was that elements all have the same number of protons. So number of protons for both of these is going to be 6 because they're both carbon atoms. But now notice that their mass numbers are different. So the way that we're going to figure out the number of neutrons in each of these is we would take 12 minus 6 is 6. Number of neutrons, we'll add that. So we have 6 neutrons in carbon 12. But if we look at carbon 14, we'll take the mass of 14 minus the number of protons. This gives us 8. So notice now there's a different number of neutrons, and therefore it has a different mass number. So these two are isotopes of each other. Uranium-235 is an isotope of what we'd normally think of uranium-238. This is the traditional, like what you might see if you just looked off the periodic table. So these two are isotopes of each other because they have different mass numbers. Here on this slide is probably my favorite definition of isotopes, and it says that isotopes are atoms of the same element having different masses due to varying numbers of neutrons. And we're going to go ahead and see that here in this table representing the 3 isotopes of hydrogen. So what we see is we have hydrogen 1, and again remember hydrogen 1, the 1 is representing the mass number, and this is generally referred to as a protium atom. Hydrogen 2 is deuterium, hydrogen 3 is tritium. And I know these words seem kind of complicated, but remember if you break them down, we look at the prefixes. Pro generally means 1, and if you think of like prophase, it's the first thing that happens, so pro is going to have 1. Then dew means it's going to have 2, and tri is 3. So if we look at this, the mass number here is 1, so protium 1, deuterium is 2, there's the mass number is 2, and for tritium, the mass number is 3. So when we look at these, since they're all hydrogen, they are all the same element. Notice that they all have the same number of protons, and they also have the same number of electrons, because we're saying that they're neutral atoms. We're making that assumption. So the idea here is we're going to look and see what we see in the nucleus when we look at these three different isotopes. So for the first one here, hydrogen 1, you have 1 proton and 0 neutrons. So when we look in the nucleus, all we see is the 1 proton. Now you might be wondering, well, what's going on with these electrons? Remember that the electrons are found in the electron cloud, or sometimes we think of them as orbitals or shells surrounding the nucleus. So electrons are not found in the nucleus. We wouldn't see them in this picture over here. The next one, hydrogen 2, we call it hydrogen 2 because it has 1 proton and 1 neutron. Remember, the mass number is equal to the number of protons plus the number of neutrons. So in this case, 1 plus 1 makes 2. And so in this nucleus, we can see 1 positively charged particle and 1 neutral or neutron there. Hydrogen 3, again, the mass number is 3, and the reason that it's 3 is we have 1 proton and now 2 neutrons. So 1, 2, 3. There's 3 subatomic particles in the nucleus, so our mass number is 3, and this is what we would see if we looked in the nucleus. When we look at elements in nature, we find that elements occur in nature as a mixture of isotopes. So we just saw in the last slide that hydrogen has 3 isotopes. Well, helium also has 2 isotopes. And those isotopes are helium-3 and helium-4. Again, I'm hoping that you're seeing the little mass number here and you're going 1, 2, 3 particles. Okay, mass number 4, 1, 2, 3, 4 particles here. And then there's also 2 different isotopes of lithium that occur in nature, and that's lithium-6 and lithium-7. Again, notice that for lithium, it has 3 protons. Each isotope has 3 protons. It's just their number of neutrons that differ. So just to review, isotopes are atoms of the same element that differ in the number of neutrons. So remember, one of the big objectives for this lesson was to be able to calculate the atomic mass. So if we ask the question, how heavy is an atom of oxygen? Well, now that we know about isotopes, we might say that it depends because there are different kinds of oxygen atoms, or there's different isotopes. So when we discuss the atomic mass, we are more concerned with the average atomic mass. And the way that we calculate this average atomic mass is it's based on the abundance or the percentage of each variety of isotope of that element that appears in nature. On the next slide, we're going to discuss the units for determining the atomic mass, and you've probably heard this before. When we discuss atomic mass units, AMUs, that's the unit that we use to describe atomic mass. So measuring the atomic mass, so instead of using grams, the unit that we use is the atomic mass unit, or AMU. And an AMU is defined as 1/12 of the mass of a carbon atom. So think of that. If I have a carbon atom, I divide it into 12 parts. Where are we getting this 12? This is from the number of protons plus number of neutrons in carbon, so 6 plus 6 is 12. So an atomic mass unit is equal to 1/12, okay, or the mass of 1 proton or neutron, and so that's where we came up with this atomic mass unit. So carbon-12 is chosen because of its isotope purity, meaning that it's pretty common, like it's the most abundant of the 3 isotopes of carbon that appear. So each isotope has its own atomic mass, thus we determine the average from the percent abundance. So like I said, one of our jobs here today is to calculate the average atomic mass. And so we're going to do that by multiplying the atomic mass of each isotope by its abundance expressed as a decimal and then add it to the results. So just a little note, if not told otherwise, the mass of the isotope is expressed in atomic mass units, and we already discussed this unit. So here's an example of how we can calculate the average atomic mass given 3 isotopes. So here we have carbon-12, carbon-13, carbon-14. Here's our symbols, and these are usually like in superscript. And notice that we're getting this mass number, or this mass number here, by adding the number of protons plus neutrons. So 6 plus 6 is 12, 6 plus 7 is 13, and 6 plus 8 is 14. So then if we look how often each of these isotopes of carbon occur in nature, so this percent in nature, we find that carbon-12 occurs almost 99% of the time. Carbon-13 only appears about 1% of the time, and carbon-14 only appears about 1/100th% of the time. And so when we look at the average atomic mass of carbon, it's not an even 12, even though that's the most occurring. We notice that our atomic mass is 12.011, and that's because we have to take into account these slightly heavier isotopes of carbon, so they will contribute or make the average mass a little heavier. So if we were to take 12 plus 13 plus 14 and then add them up, we would come out with a number, and then divided by 3, we'd come out with 13. But notice, since we're taking into account the percent abundance, how often they occur in nature, our atomic mass is closer to 12. And we'll see a little bit more of that on the next slide. So here's an example problem. So we're going to say that element X has 2 naturally occurring isotopes. The isotope with a mass of 10.012 AMUs would be referred to as X, so 10X, and it has a relative abundance of about 19.91%. There is an isotope with a mass of 11.009 AMUs. It has a relative abundance of 80.09%. So calculate the atomic mass of each element. So even before we get started, let's go ahead and take a look at this. So I've got 10.012 AMUs, and it occurs close to 20% of the time. Then I have another one that's 11.009, about 11, and it's 80% of the time. So if we were to make an estimate quickly before we made our calculations, I would say that the atomic mass is going to lean more heavily towards 11 than 10 because of the higher percentage of this 11 isotope occurring. So we want to go ahead and list all of our knowns, and we're doing that here. Then the thing that we don't know is the average atomic mass. So what we're going to do is we're going to take the mass for each, we're going to multiply it by its percent abundance in decimal form. And so to get this into a decimal form from a percent, we're just simply going to take the number. So in this case, let's take 19.91%. We're going to divide it by 100 to get rid of that percent, and we come out with 0.1991, and notice that is the same number that we see over here. So when we do this math, 10.012 times 0.1991, we come out with this AMU. We make a similar calculation, come out with a number, and then when we go ahead and add them together, we come out with 10.810 AMUs, and notice I said it was going to be closer to 11, and 10.8 is closer to 11 than 10. One of the other objectives we had for this unit was to do a preview of the periodic table. And so a periodic table is an arrangement of elements in which the elements are separated into groups based on a set of repeating properties, and that's going to be really important. These properties are going to be distinguished by the number of electrons in their valence shells. So determining the number of electrons is going to be very important in the next section. In addition, the periodic table allows you to easily compare the properties of one element to another. So we're going to see some shorthands later that we can use. Something that you definitely want to know is that each horizontal row, and there's 7 of them on the periodic table, are called a period. Each vertical column is called a group or a family. And that elements in a group have similar chemical properties, and I told you that's because of the number of electrons in their valence shells. And we can identify these with a number with either an A or B. So when we look at the periodic table, and this is just obviously like a rough sketch here, so these in the middle here are B's, here's our A's and A's. So take a look at your own periodic table, and you'll see it says like 1A, 2A, and there's Roman numeral 1, Roman numeral 2A. And then, like I said, we'll talk more about this in Chapter 6. But the highlights here is if we're going across, we call it a period, and if we're going down, we call it a group or a family. That's all, folks. Remember that if you do have any questions, please bring them to class because your classmates probably have similar questions.